particular also to the committee for this invitation to give this presentation. So, as was announced, we were interested in these active crystals in the self-propelled particle crowds. And there is one question that particularly interested us. That is when you suppose you stack the self-propelled particles on a regular lattice. So just by this stacking, will they find the common migration direction so that this whole structure can collectively migrate as a single object? So that is the scope. So let me first motivate a little bit this from biological systems. So here I took this from a biological paper. What you see here is a pattern, nice pattern from colonies of marine bacteria. And these marine bacteria are active in the sense that they have these flagella, they can beat and set the water into motion. This scale bar here is 0.5 millimeter. So actually you see many bacteria. You can't see the single bacteria. And what is bright, the bright color, are the bacteria, and these black holes that you see is the substrate that you can see through the colony. It's grown practically in 2 dimensions on the substrate. And this is, well, it's not completely regularly ordered, but you can see here one hexagon, here's another hexagon, and so on. So taking into account how many bacteria these are, it's quite impressive that they can form this structure, and we could call it honeycomb texture. When you're interested in these pattern formations, and you see this honeycomb texture at this density, then you might guess that when you now decrease the density of the bacteria, there might a lamellar texture appear, and actually they did this experiment. So they reduced the mean density, and they now find these stripes appear. Again, not completely ordered, but we can accept this as a lamellar texture. And if you still further decrease the density, you might expect a hexagonal structure. That's not really hexagonal, but still we can see these localized clusters. Many bacteria in one of these spots are well separated from the other spots. And now when you do a density description of something like this, you might say, okay, there where there are no bacteria, density is low, and when you go into the domain of many bacteria, density becomes high. So one density peak, many bacteria.
Are the bacteria moving?
So these, they are practically not moving here, but they have the flagella. When they are alone, they probably can move.
But they're stuck, but they're moving the medium above them or around them.
Yeah, they set the water into motion.
Set the water.
Yeah. Okay. So that was the one case. And this is the other system. This is now the artificial system, the Janus particles. So we have the Janus particle, one platinum cap, for example, that here in the peroxide solution leads to the catalytic reaction, and then these particles start to self-propel. And now we are really interested in the single particle. And again there, for example, the density functional theory teaches us that now you can also identify one density peak with just a single particle on the diffusive time scales. Okay, and here they propel around. We already saw this clustering in the previous talks today. They form these dynamic clusters, dynamic in the sense that particles can attach and detach again. And what was shown in these early simulations. So you can get such a system very easily. Everything you need is a steric repulsion that is isotropic. So these are round disks that isotropically interact. And then there is one direction of self-propulsion that can diffuse in space. And this is enough that these clusters emerge. So such systems were further studied in bigger systems than recently in the Bechinger group in Stuttgart, and also numerically in our group. And what comes out when you look in the center of these structures, they can be quite regularly arranged, so really a hexagonal structure. And that's why we think that this crystallization in these self-propelled particle systems is certainly conceivable. When you go to high enough densities, they will have to arrange if they have these steric interactions on hexagonal structures. And if they, in addition, attract each other, then they will certainly form these active crystals or stack on a regular lattice that for our purpose we call the crystal. And these are these structures that we're interested in. For this purpose, we introduced this active phase field crystal model that I will briefly introduce again. And then there comes this main point. Will these structures then start to collectively migrate into one direction? And very qualitatively, we also introduced some hydrodynamic interactions to check what these will do. Okay. So, our approach is based on this famous phase field crystal model that was introduced mainly by Elder and Grant a few years ago for equilibrium systems. So on diffusive timescales, they wanted to model periodic structures that have periodicity in space as easily as possible. And then they use this energy functional for this purpose that has a one scalar order parameter, density. So here the mean density, and this psi1 is then the density modulation around this mean density. That appears here in a quadratic term with this temperature variable, this epsilon. So decreasing the temperature would lead to a sort of phase separation. We have the stabilizing quartic term, and the key here is this red term. So you can see this has a squared, so this is always positive. This always leads to an energetic penalty unless this Laplacian here can pick out a wave number that is just equal to 1, because then this term will vanish and no energetic penalty arises. So in that sense, this term enforces periodic structures on length scales with wave numbers that are here normalized to 1, so really through the whole space. And then they just study the diffusive processes in this relaxation dynamics with the conserved order parameter. And just here's the phase diagram of this earlier equilibrium study. So here's the temperature, and here we have the density. High temperatures is a constant phase. Come to this in a second. And if you cool, you can get these hexagonal, lamellar, or honeycomb textures, just the series that we saw previously for these bacteria. Okay, and now the explanation how this is interpreted. So here you can see a snapshot. There's a background that is one color. That is the constant phase. And this is interpreted as the probability to find a particle. So here in the background, the probability to find a particle is everywhere the same on the diffusive timescale. That's why we identify this with the liquid. And then we have here these areas where there is now periodic modulation with the density peak. Density peak means, in this case, high probability to find a particle. So in this sense, we have here crystalline regions. And what they did here in this paper, just to model the nucleation process, they supercooled from the liquid into the crystalline state with 3 nucleation sites. These grow and then form these multi-domain structures. Okay, so this we took as the basis, and then we added the activity. And the way we did this, we got inspired by this famous early Toner 2 model. So we introduced a new order parameter, or a further order parameter. This is the diffusive equation you saw before, and now what's appearing here, this V naught, is the self-propulsion velocity. And this is really the velocity put in at the single particle level, so for the single particles. And in addition to that, we have a polar orientational order parameter field, this P, that gives the ordering of the self-propulsion directions of the particles. And this then also needs a dynamic equation. Here we have translation and rotational diffusion. And here's the Toner 2 input, this energy functional. If these coefficients C1 and C4 both positive, that means this likes to depolarize. So the order parameter likes to go 0. In that sense, these diffusive terms would counteract spontaneous ordering of the self-propulsion directions. If this C1 goes negative, then a spontaneous orientational order can appear. And this is sort of alignment mechanism for the particles to migrate into the same direction. And to couple this back, we here have again this term, the self-propulsion velocity, like the pressure term in the density. Okay, so first there is no reason not to write down this equation from the symmetry arguments. The reason why we chose this form is because this one we can also directly motivate from a more microscopic approach. Very crudely, from the dynamic density functional theory, you start really on the one particle level, the one particle density distribution function. So this here is proportional to the probability to find at a certain position at a time a particle with a orientation u that is really its direction of self-propulsion, and there at the single particle level we put in this active drive. So it's really based or connected to the microscopic level, and what you have to do to systematically obtain this equation is to expand it around the orientational ordering. So here is the mean density, this is the scalar order parameter, the density modulations, And then you see in the lowest order of the orientations, we get this polar orientational order parameter. So that really gives us the ordering of the self-propulsion directions. Okay, that was briefly the model. Of course, we also here determine the phase diagrams. So this is the check, 0 self-propulsion velocity, so no activity, and we should reobtain this phase field crystal phase diagram that you already saw before, and we do. Now we call these phases resting lamella and resting crystalline, because as you see, they will also be able to travel. Now when we increase the drive, so this active drive of the single particles, and we will look now at the case where there is no spontaneous alignment for the single particle self-propulsion directions. So we see one positive. And what happens at first, at the low self-propulsion velocities, we get a shift of this whole thing that is proportional to the self-propulsion velocity of the single particle. So this whole phase diagram is shifted down in temperature. How can you interpret this? If the particles diffuse around at a certain temperature and you just put a little bit of drive to first order, you just make them quicker. It's just like increasing their temperature. So then you have to cool further to make them crystallize. But when you go to still higher self-propulsion velocities, then these density peaks start to migrate, and now we call these traveling crystals and traveling lamellae. And there is another effect. You see that the self-propulsion makes this lamella region eat up the crystalline region. So crystals are destabilized of the self-propulsion and the lamellae are favored. Okay, so now a little bit more illustrative maybe. So these are snapshots from different systems obtained like this, and increase the active drive of the single particle in this order. Red is the density, so the density peaks the red color, and then you see these small needles, these turquoise needles. This is this polar orientation order parameter field. And this is by construction on diffusive time scales. Now if we take such a density peak in this state and we average over this polar orientation and order parameter field, so the probability to go in a certain direction is the same everywhere, symmetric configuration, so it will stay at rest on average. So we get the resting structure, and then if we increase the drive, there appears the symmetry breaking that is characteristic or necessary for all this self-propelled system. Now these peaks are shifted out of the symmetry center, you average over one of them, and you get the next direction of self-propulsion. So now our structure travels. And with increasing drive, what we found is hexagonal structure is continuously deformed to a quadratic via intermediate rhombic states that also travel, and finally, as you also saw in the phase diagram, the lamellae appear that migrate always perpendicular to their elongations. So nicely, our equations are invariant under this operation, so inverting all densities and inverting all directions. We have the same equation, so with the resting and traveling hexagonal structure, we simultaneously capture also the resting and traveling honeycombs, and also the quadratic gives the inverted quadratic, and if you invert lamellae, of course you're back with lamellae again. Okay, that was the overlook, and now a little bit more quantitatively. So this question of onset of collective motion. So for this purpose, we measured the speed of the density peaks. So in the numerical sample, we tracked the motion of the peaks for each peak, and then this is averaged over the whole sample. And this here is then this blue curve. This is the peak velocity plotted versus the active drive of the single particles. So the peak velocity in the structure versus how quickly a single particle would propel. And what you see for this case, where C1 was positive, so no spontaneous orientational ordering, there is a finite threshold. So at low self-propulsion speeds, there is no collective migration, but by organizing this in this lattice structure, and by increasing the active drive of the single particles, you will find a finite threshold when this whole structure can start to migrate. Because if you have an alignment mechanism, so the point is negative, then there is no such threshold, then already directly from the zero you can start selective migration. Along this curve there appear these snapshots that I've shown before. So here's the resting hexagon, here's the traveling hexagonal structure, and continuously this deforms to quadratic structures. And then there is a drop in this curve, and here we have the traveling lamellae. So where is this drop coming from? So this drop you can simply explain by geometric arguments. When you think that this traveling quadratic structure is made up of overlaid perpendicular oriented lamellae. So you have two lamellae, they are perpendicular, overlay them, and there are intersection points. And by simply geometric arguments, you find that these intersection points migrate then by square root of 2 quicker than the single lamellae. And that roughly corresponds to this drop here. Just above this threshold, we get something a little bit more exotic that we call the swinging motion. So this is this inset here. These are trajectories. So each color is one peak. There is a row of peak initially, and then they migrate over time. They make these wavy swinging motion. Maybe a short movie on this. So here's how this generally looks like. It's a hexagonal structure, and in this case we have one of these wavy motions. And the funny thing is that we could wait as long as we wanted. This never disappeared. And also when we went to much bigger systems, we could still find it. So also, it's not clear if this is a finite size effect. So, okay, and finally the question, is it really a collective motion? Does this crystal move as a whole into one direction? So we measured this polar order parameter. So for each density peak, the direction of migration, and then this polar ordering over the whole sample. So this P here would be 1 if everything moves in the same direction, if all peaks go in the same direction. This is plotted here, and this is this purple curve. You can see already at the threshold this jumps to values close to 1. So we can say yes, so these objects really migrate collectively into one direction. Okay, finally, so at each data point, to obtain these points, we start from random initial conditions. Of course, the system does not give us then already the traveling single crystal. There is coarsening involved in this, and these are depicted here. So starting somewhere here with random initial conditions, you find over time here a series of snapshots. This corresponds to a hexagonal structure. There appear lines because these are trajectories, not the structure itself. So at a certain time, we jump into the system, and then for each peak there, we track the motion, and each of these trajectory pieces is plotted here in a different color. That's why all these colors come. Each color is one peak. And where they migrate in the same direction, we get one domain of these drives. They connect to these lines. So each domain here corresponds to one domain of migration direction. And this coarsens over time. Finally, this domain will also vanish. And then we will only have these defects left. And these take a long time. So there's another movie here. Start from the random initial conditions. These density peaks form. They start to migrate. Initially, there are different migration directions, but finally, all of this will move into one direction. And of course, if you have a bigger system, it takes longer until you have this motion into one direction. Still, you can see there are defects in the sample, and these take them longer than we want to wait to get out of this. Okay. Yeah, and in the end, briefly, the hydrodynamic interactions. So very qualitatively, what we did, okay, this was in 2 dimensions so far, and we assume that these particles still migrate or propel close to a substrate. So the important point is then they exchange the momentum with the substrate. And now we assume that we have a surrounding thin film of fluid, and these particles can migrate in the fluid and push the fluid. So we need a flow field, this is this U. We have these additional convective terms now on the rotational part, this vector order parameter. So this flow field U, for simplicity, incompressible in 2 dimensions. because we can drop this nonlinear term with the low Reynolds number. So immer, this F here is the force term, where we say this is the contribution when the density peaks migrate, the particles push the fluid. So we track the motion of the density peak and set at each position of the peak, we set the fluid motion equal to this peak velocity. And to mimic the presence of the particle, we get inspired by this fluid particle approach by Tanaka and Araki. So they vary the density, the viscosity with the density. So small density, low viscosity, high density, high viscosity to mimic the presence of the particles. And finally, there is this friction term. So when the fluid film flows on the substrate, there will be some friction. This alpha is our friction parameter. Alpha very large means that this velocity will vanish. Then we are back in the previous case with equations decoupled from the velocity field. So this looks like this. So here we are at high friction. Here the density peaks, they migrate to the bottom left. This is the velocity field, and you can see it's very localized at the peak positions, where the peaks push the fluid. Does not extend between the density peaks, so it finishes in between. So there is little hydrodynamic interactions between these peaks. Even when we rescale this, then these backflow regions appear around the peaks. And if we decrease the friction, then more and more these particles can set the fluid into motion. Finally, this whole fluid flows, and then there's of course a stronger hydrodynamic interaction. So the flow extends between the peaks. And what happens? So one peak pushes the fluid pushes the next peak. In that sense, they can support each other in migration. So here we plot again the speed of the peaks versus the active drive of the single particles. The red is with high hydrodynamic interaction, and the green with low hydrodynamic interaction. So this supporting the peaks through pushing the fluid leads to a speed up of the migration. And another thing is that this drop appears earlier. So in that sense, with a hydrodynamic interaction, destabilize the crystalline structure. The last point here, you can see this also from these snapshots. So these are completely identical system. All parameters are the same. The only thing is here we have the high fluid friction. That means low hydrodynamic interactions. That gives us a perfectly crystalline domain. But when we increase the hydrodynamic interaction by decreasing the fluid friction, then these remaining domains are differently oriented. Already the lamellae appear, so the crystal is destabilized. So that's all I wanted to say. So in summary, we introduced this active phase field crystal model, where we could describe these resting and traveling crystalline structures. So the key point is the second line. Even if we do not have an alignment mechanism for the self-propulsion directions of the single particles, through this organizing in this elastic structure, there is a threshold above which still this whole texture can start to migrate collectively. And as we saw, the self-propulsion as well as the hydrodynamic interactions, they destabilized these active crystals and favored lamellar structures. Acknowledgements at the end, of course, to Hartmut Löwen, with whom I worked on this. I had several valuable discussions with Professor Takao Ota from Japan, and we are supported by the German Research Foundation. So, thank you very much.
How could you motivate, in few words, your original equations with this variational derivatives, even without fluid? Why this free energy? Why is it taken from somewhere for some reason? Or
okay, so the start is this one.
Yes.
Was this input?
Why this free energy? Why not to write something else?
Okay, so first because it works.
Yeah.
And the second is, so meanwhile, okay, so when we really take a strong microscopic theory, like density functional theory, so this, meanwhile, they have established a connection to this energy functional. So there are several papers on this. So it has some foundation, and so that is this first part. And then actually, if you systematically do this derivation from the density functional theory, including now the orientational order, so that is This is like a density functional theory for liquid crystalline materials. And you do this systematic expansion, then you really get to these equations.
In this equation, if you even put F0, it will be wave equation out, yeah?
That's,
You
so
exclude
if you have there you see directly
you
the
have
lamelli.
hidden wave
Yeah, yeah.
structure, wave propagation, yeah?
So that is the limit when you have very, very high velocity of the single particles. And you see it's directly the wave, and these are then these lamellae that we saw for the very strong drive.
I see. And where from is the directions? Finally, you have solution that all crystal move to somewhere. Why this direction? Why not the opposite? Why? What?
Well, that's a symmetry breaking. So it chooses by the coarsening, it chooses one common direction in the end.
Occasionally, just randomly, yeah?
Well, it depends, of course, on because this is a mean field description. There is no noise. It depends on the initial conditions, or the noise is in the initial conditions. So from this, numerically, it gets the final direction is prescribed in the initial conditions, but of course the initial condition is random. So in that sense, it's really spontaneous.
Okay.
I'm interested in the regime of coarsening that you showed. Have you tried to identify any scaling laws associated with this coarsening process?
No. We have only qualitatively looked.
So what's holding you back? Is it computationally intractable to simulate in a large enough domain to get that information?
Yeah, it would be some next step. Yes, it's a good thing to do.
Are there any conjectured scaling laws?
I mean, it's a mean field description, and maybe you get something from this, but on the other hand, you have these convective terms. So I wouldn't want to make a statement on this. Yeah.
I didn't understand how. Can you just go a couple of slides forward where you show the further? Next, no, where you show your phase. Yeah. So these phase diagrams are calculated using what criterion for selecting a state? It's a non-equilibrium problem, right? So
Okay,
how
so
do you decide when?
So these are numerically obtained.
Completely numeric.
Completely numerically. So
I
we
see.
simulate for each point system for several different random initial conditions, and then there's a numerical routine that checks if which sort of texture this is, and
you find there's in each region there's a unique stable stationary state. Is it? Doesn't depend on the initial conditions.
okay, so
And you might expect, since the transitions were to begin with were discontinuous, you might expect coexistence, in which case...
okay, so that I didn't mention, and you see it, this, for example, here, this is not perfect. So at these phase boundaries, there is some coexistence, and then we just take the majority of phase that we see. But we do not resolve these. So there are coexistence regions that should be resolved if you're more exact, but here we did not do it in this first approach. And this is what in the equilibrium phase diagram is these hatched regions. That is the coexistence region.
Okay. Question.
The length scale that you get in lamellar phases, crystals, and so on, so the characteristic size, which is bigger than 1, what do those length scales depend on, say parametrically, when you change something?
So I do not exactly understand the question. So this.
So say you show one of those patterns,
Yeah.
yes, for example here.
So this is really the wave lengths that you put in. Is what you see in the red. That's the input wavelengths.
So this is controlled by this C4, C2, those coefficients.
This
that
is
right?
controlled by the one that you put in here, the rescaled wave number that is put into this model.
So one block is 1 unit of length for you, is that right?
So
One lattice. So then my question is, how can you resolve what's in it? I was a bit...
So, I mean, it's a field description. So one peak has maybe here, I don't know, 10 lattice points of the calculation grid. You mean because there are many more needles, many more of these turquoise things?
I'm just trying to understand the basic unit of your real system, which would be described by this. Is that one of these red spheres, or is it...
So the basic unit is in principle from one peak to the next. That is
Okay.
the input wave number.
Okay, thanks.
Okay.
Nice, speaker again.
Okay. Thank you very much.